I want to carry on from where I left last year. Those who came to the talk, we talked about a giraffe, which had this race with a gazelle, and clearly enough, it managed to warn the gazelle that it shouldn't go in a certain direction, did not listen, then in the end, it lost its life. So today, I'm going to continue from there. The same giraffe continues the water hole as another day and finds a frog, but it's taking the water and then realizes there's a croaking sound. And then jacks out a little bit and then looks around and sees the frog just sitting there in the water and asks you, Mr. Frog, what are you doing? Then the frog says, well, you know what? I'm just looking out to the skies and I'm just wondering how I could get over there in blue skies and explore. Can you give me a ride? And then, yes, but you have to let me take the water first. Once I take the water, then I can give you a deal. Okay, I'll make you a deal. So the giraffe continues taking the water. And then once it was finished, then asked the frog to ride on the head. So the frog jumped right on top and then lifted its hand all the way. And the frog was mesmerized. It was looking out to see greeneries and beautiful sceneries and said, Mr. Giraffe, man, you got nice views right here. And then it looks towards the water hole and then immediately sees the skies there and realizes, oh my God. So even the skies are much closer. So I'm going to dive right there. So the frog leaps out and goes all the way into the pool. And then said, this ripples around and the giraffe is like wondering what is going on, looks out and say, Mr. Frog, my God, you are in heaven. Because you could see these beautiful waves, propagating outward. So today, I want us to take a ride on John Mather's shoulders, like the frog. And we're going to try to explore the universe. As some of you know, of course, he's been working on JWST and leveraging what he did last time. Is where he talked about his life from childhood all the way to the time he got the Nobel. So today he's going to continue with that journey on part 2. And we are going to explore on his shoulders the future of JWST, and the future of the universe. Please help me welcome our Nobel winning scientist, John Mather.
Thank you for inviting me to come back. There's always more stories to tell. I think I told you my life story last time. I might have even been wearing my giraffe tie last time. I have this sort of affinity with giraffes, you might imagine. At any rate, today I want to continue on and talk about where we're going with the James Webb Space Telescope, how we're getting along with it, and the ambitions that many people have for what we might want to build afterwards, which is obviously bigger and more powerful even than the Webb telescope. So this chart set that I'm working with today was assembled to explain first to the Space Symposium out in Colorado Springs last summer, and then again at NASA headquarters, why it's a good idea to search for life out there, circling other stars. And so I want to illustrate that story for you. Let me start with some of the obvious things. The Hubble Space Telescope has opened up an enormous territory for us, and obviously enough also is only 100 inches across, the same size as the Mount Wilson 100-inch telescope that we built over a century ago. And so we have a little ways to go to catch up in space to what we can do on the ground. So a 100-inch telescope, 2.4 meters, is a spectacularly powerful telescope. It's more powerful than it's ever been, still working beautifully. And as everyone also knows, it required astronaut intervention to repair it and to continue to upgrade it. We've been up there 5 times to do so. So what are we going to do to follow that? Let me step back in history. This is Edwin Hubble, the man, over here on the left, looking through the telescope. And he was, back in 1929, he gave us this little graph that showed that the universe is expanding. I think I told you last time about how this was a huge shock to most astronomers and most of the public to see that these galaxies, each of these things is a dot is a galaxy going away from us at a speed proportional to the distance. divide the distance by the speed, you get the age of the universe. 2 billion years, according to his measurements. That was incorrect, which was very difficult for people to understand for a while. It was incorrect for a number of reasons, but the consequence was people thought, well, that's crazy. We eventually know that there are objects like stars and the Earth and the Sun that are older than the universe. Something's the matter with the big picture of the expanding universe. So we had some pretty revolutionary concepts invented in the meantime to go along with those conflicting bits of data. So it took about 50 years for us to really finish that job using the telescope that I just showed you, the Hubble Space Telescope, to finish the job that Hubble started, figuring out the age of the universe. So now we know it's 13.8 billion. So another beautiful picture to show you. I love these pictures from Hubble. This took about 2 weeks for the Hubble to take this picture. And what we see are thousands and thousands of galaxies in a few square arc minutes of sky. So if you could actually take a picture of the entire sky with that same degree of exposure, you would have hundreds of billions of galaxies that you could just see with the Hubble telescope. Of course, we don't have many thousands of years to do that, so we're not going to do the whole sky catalog, but just the representative bit. So then we are led from measurements that we have taken with the Cosmic Background Explorer and with the WMAP mission, which produced this lovely graphic. We now have a story about the expanding universe that we started with quantum fluctuations. This is a pretty shocking idea, but it actually has support from measurements that the universe kicked off 13.8 billion years ago with quantum fluctuations in some primordial material that included a kind of anti-gravity that would make even space itself would expand exponentially. And that lasted for 10 to the minus 30-something seconds, roughly speaking. But kicked off the piece of the universe that we now have so that it has all the features that are now in it that we see. It gave us the quarks and the gluons and the leptons and all the particles. It gave us dark matter. Hidden inside at the time, although it probably didn't make any difference then, was something we now call dark energy. And that's what the artist has sketched in with the fact that the expansion seems to be accelerating up here. So the features that we are now tracing through astronomy date back to quantum fluctuations of some primordial substance. And this is a totally astonishing story, which nevertheless is testable based on the measurements that were made with the WMAP and now again with the Planck mission, which is about to report its next generation of data. So we have this totally amazing story about the early universe. Then we have the sort of astonishing miracle that here we are. Our little ball here, circling a little ordinary star, has us on it. And how did that happen? Well, there's a lot of stories to tell, and obviously we don't know the answer. So I like also to illustrate where we are in a different way. This is not our galaxy, this is somebody else's. I say somebody because I kind of imagine there are sentient beings out there, but I don't know. So here's the middle, probably has a black hole in the middle because all the big galaxies do. And the different colors here are telling you that stars are being born as we speak. The bright blue ones light up the clouds like that. The red ones are a different chemical being represented here. The dark lanes are interstellar dust, which block the starlight from coming. So that's also important because we ourselves are made of that kind of dust. Stars exploded, blew material out, it turned into dust. There it is. Some of it fell back in, turned into stars and planets. So that's our cosmic history. Also astonishing story. The atoms we're made of have probably been blown all the way out of our galaxy, maybe came from another galaxy even. So you're looking at interstellar, intergalactic travelers already. But those atoms don't remember where they were. So anyway, what else do we see? We now have a simulation of the early universe. This is a simulation that came out last summer called Illustris. And it was made with supercomputers. And what we do is we take the random numbers that we think the universe was generated by in the early universe, the quantum fluctuations, represent those random numbers by particles in the computer and let gravity work on them. Gravity works and pulls the material together into this amazing collection of stars and galaxies. At first, it's the dark matter that we know of that works and pulls everything else in. then dark matter cannot make a star, but the ordinary matter can. So eventually the galaxies start to turn on. There are explosions happening. Explosions for two reasons. One is stars blow up, they explode, and produce the chemical elements that come back out. The other is down in the middle of a galaxy is often a black hole. Black hole sucks material in. Material that gets sucked in gets very compressed. Some of it squirts back out again in jets of material. And so this spectacular process has now been simulated. And it is claimed that this now resembles the real universe that we have observed. To be proven, of course. There are many detailed predictions of a story like this, and when you take a picture of the sky like the one I showed you, it doesn't look like that. We don't get to watch 9 billion years worth of movie in one picture. What we do, though, is we look back in time and we see things as they used to be. So we see, if we look out 9 billion years, it's like looking back 9 billion light years, it's like looking back 9 billion years in time to see the universe as it used to be, and we should be able to compare the pictures that we take with synthetic pictures that you can make from the simulation. So eventually we might know if we got about right. You could say, well, isn't this so wonderful that why don't we just run the movie? And the answer is the computer people say we'll never get it right until you observe. There are too many things you cannot possibly know. The computers are just not powerful enough to do everything for us. But isn't it amazing and beautiful? So the universe starts to sort of quiet down after the first 9 billion years, which coincidentally is the time that the Earth and the Sun system were formed. So something to be found out if this is true. So a lot of people worked on that movie. And I'm sure there will be sequels. So what does it look like closer to home? This is the beautiful Orion Nebula, which is one of the few places you can see with your own eye where stars are being born today. This is the middle of the sword in Orion. And so lots of bright stars. If you took your binoculars out, you see a handful of stars. Big telescope sees many, many more. You take a Hubble picture and you see the glowing gaseous material. And that's material that is being lit up by the stars. Some of it is turning into new stars. So it's where every astronomer always turns a new telescope. I'm sure it's going to be on our list for the James Webb. So now I want to tell you how we got the Webb telescope started. So in 1995, Hubble had been repaired. A committee had been formed to advise NASA about what we should do. It was called the HST and Beyond Report, HST Hubble Space Telescope. And Alan Dressler was the committee chair. So what they wrote is a beautiful little book, very poetic, and when you read it, you're just inspired that you must support this, we must be able to do this. So, but the committee was cautious. They said, well, we don't know how big a telescope we could possibly get, so we think we should ask for a 4-meter telescope, because you can imagine getting a 4-meter telescope into a 5-meter diameter rocket, if you were really good at it. So, so he went down to see Dan Golden, who was our administrator of NASA, and they met and they had a good time. So a few months after that, Dan Golden went to the Astronomical Society, which not very many administrators will do, and he told the astronomers that we're going to build this thing that Alan's committee asked for, but why did you ask for such a small one? And so he got a standing ovation. So that was our first peer review. And so we knew that astronomers would be thrilled if we could do this. Eventually they got cold feet because it seemed expensive, which it is. But nevertheless, it received top priority in our 2000 decadal survey that we do in astronomy. And again, with the 2010 was built around it. So we know that we're doing what the community asks us to do as their top priority. So we now have an international partnership with NASA, ESA, and the Canadian Space Agency working together. All are chipping in their parts. So this is just to illustrate how our telescope compares with the old one. This one's still working, and it's beautiful and brilliant and does things that this one cannot do. This one will be bigger and do things that this one cannot do. So this one covers the near UV, visible, and near infrared wavelength range. This one covers infrared beginning at 0.6 microns, which is about the wavelength of the laser, out to 28 microns or so, where human beings emit huge amounts of their own infrared power. So that's what we want to do, what we're in the process of doing. So just to illustrate what this requires, there are 6 of our mirrors in the test chamber at Marshall Space Flight Center. This illustrates how perfect they have to be. If you would spread one out to the size of the continental US, the ripples would be 3 inches in size. So pretty amazing technology. And this has to be true after the thing has been cooled down to the operating temperature of 45 Kelvin. So this is one of those things where people laughed at me and said, you'll never be able to do that. But we turned the world of optical technologists loose. We had competitions, and we selected the winner, and it turned out to be beryllium material to build these mirrors. It was almost impossible, but not really. Just hard. So anyway, we got them. They're all in their canisters up in building 29 up on the mezzanine. So right now you don't see them. I think we still have another few weeks where you can see a couple of the practice units installed in the big carbon fiber frame that's about to be sent down to Johnson for the testing out that process. So anyway, it's here. That hardest part is done. Here we are just illustrating the smaller mirrors as well. They're all done. And they've even measured the optical surface quality of each one, and they're all good. So we have to have this truly gigantic sun shield. This is how big it is. It's as big as a tennis court, singles tennis court. And we have learned how to fold it up and unfold it. This is not the very latest movie that we have, but we've actually gotten a full deployment of the full-scale real thing, a test unit, not the flight one. So we know that it does unfold. We have tested our instrument package. All 4 of them have been delivered and installed in our big vacuum tank in building 7. They were lowered in last spring, tested out in the vacuum cold. They finished the test. Everything was as expected. We pulled them out. We have hundreds of little things to fix, and very, very happy with the result. So that part is done. Here you see a rare event. You actually have the dome open on the top of the tank with things going in or out. So this only happens a few times in a lifetime that you see the top of that tank open. So where will we go after this? We will take the equipment down from Goddard and put it in the tank in Johnson Space Flight Center. So there is the tank, the door, and this goes back to ancient times. The Apollo. We had to find out if you could get out of the Apollo into a vacuum and step down the ladder onto the surface of the moon. So that's what they did that for. This is on the historic register because that's historic. We got permission to improve the chamber by putting in refrigeration, and our Webb telescope will be on the right-hand side, occupying most of the tank. Telescope at the bottom, test equipment at the top, and that's what it takes to find out if it's good enough. So then we will launch it, and it will go out into space roughly October of 2018, and an amazing array of deployments will occur. This is a new movie. You haven't seen this one before. All kinds of maneuvers are required to keep this thing at the right temperature relative to the sun that's coming in. We need to keep the sun off of certain things, and anyway, first comes out the solar panels, then we unfold the telemetry dish, then we wait a while. Eventually we will unfold the protective sun shield, all done by remote control, and this is one of those scary things, because when you count up the number of mechanisms, there are literally hundreds of things that have to work correctly. Most of them are launch locks, little things that lock things into place to protect them during the launch. And then there are still quite a many of the motors and pulleys and gears and hinges that are required to finish the job here like this. So we got to practice this out of town. So we're doing that. We have tested the unfolding of the sun shield in the lab, and we've tested even the last step of unfolding the telescope itself. Nevertheless, extreme care is required. For instance, you have to make sure that the same people do the last assembly that did the one before, and that nobody forgets anything. And we do it exactly the same every time. So in this sense, our job is a kind of performance art. It's not just we are really smart, we have to do it right. So here we are. The last step is to unfold the secondary mirror and the wings, and that takes about 2 weeks before this is all done. And after that, we wait 2 months before it is cooled down to the right temperature, and then we can continue setting up the telescope. 4 months after that, we're ready to take full scientific data, and your friends who have submitted proposals will get a chance to get their data. So that's what happens in 2018. So I showed you this picture earlier. This is just another zoom into it, but this is the infrared version. And so we have seen galaxies that are extremely far away already with the Hubble Space Telescope, and we expect that the Webb telescope will have much, much sharper images than this because it's bigger. We will be looking into dusty clouds like this one, where this is an actual Hubble picture, but there's a star being born inside this one. When you go to the infrared, you can begin to see inside this cloud as well. The animators have made use of actual information about how far away the real stars are, so this is sort of realistic. But here's the infrared view of that same spot. There's a star in the middle being born, and it's squirting out jets of material too. Just sort of like black holes do. But as material is falling in, it gets compressed, some falls in, some gets squirted out into these jets. So that could have been the history of the solar system, and we're not sure yet. Eventually, other things happen. Stars look like this. Here we see the jets of material coming out, and in this direction is the plane of the orbits of the new solar system. So wouldn't we like to know more about this? So yes, of course. We have in mind a whole series of missions that already have been done or will be done to study planets around other stars. Hubble took pictures of at least one planet orbiting its star already. You see the little dot and you see it move from year to year, and you can even get the orbit of that planet around that star. Spitzer doesn't actually get a picture of those planets, but it has seen many, many cases of a planet interrupting the starlight, or vice versa, star interrupting the planet's light. The Kepler Observatory has counted many thousands of transits where a planet goes in front of the star, and about 900 of those are confirmed as real planets. Some of them are a lot like Earth, but not exactly yet. So anyway, we have a big catalog to follow up to find the most interesting ones. We have decided to build the TESS, the Transiting Exoplanets Sky Survey, I think is what it is. Anyway, it's a small observatory, but it will look for all the nearest, brightest ones of these transiting planets. So those will be the best ones to follow up with another bigger telescope. So then we'll put up the Webb telescope. We'll follow up those targets. And we'll say, aha, I see something there. Let's find out more about it. After this, a couple of more things are possible. We know that NASA has basically set off to do a wide field sky survey with a bigger telescope, 2.4 meters probably. This is leftover spy equipment that we will probably reconfigure. It's not finished, the planning for this, but probably. And it will even have on it a coronagraph, which is a device that we use to look for planets orbiting around stars. Finally, let's think about what we would build after that. Well, there are so many different names for it. Here in this one, it's called the New Worlds Telescope, but I'll show you various things that we might want to do for that. So, lots of stars out there. Some of them might have planets. By the way, there's that Milky Way with the dust in our own Milky Way. Keeps us from seeing the middle of our own galaxy. But that dust is like the stuff that makes planets, too. So there are lots of planets. And what the Kepler Observatory has been able to tell us is the statistics. And what they show, here's a graph of planet size relative to Earth. And in the smallest planet category, about 12% of stars have a planet about the size of Earth, maybe a little bigger, and the smaller ones are more common. So we don't know how many Mercuries and Venuses there are, but the big ones like Jupiter, they're not that common. And also, well, anyway, the systems are different, but there are a lot of medium-sized ones like Neptune. Anyway, lots of stuff to look at. And then we can also calculate how many of those planets would be at the right temperature to be habitable. Not to say they are habitable, but how about the temperature at least? So basically between Venus and Mars is where we are, and it's too hot on one side, too cold on the other. So let's look for other solar systems which have roughly that sort of dimensions. So how are we going to go at it? Well, we can use what we've got and what we're already planning, and we can imagine building something bigger, better, and more powerful to do this. So it's pretty clear that we cannot count on seeing an Earth-like planet from the ground. It's just too dang hard. The Earth's atmosphere shimmers, the planets are too faint, all that. So there's a reason why we didn't already do that. It's probably impossible. Well, sometimes impossible things can be done, but probably best to try the space business. So here's a picture of the Tess Observatory, and it's actually not your big telescope. This is small cameras, small wide field cameras, so you can study the whole sky. Not all at once, but as the thing orbits the Earth, you can cover the whole sky several times a day, see if anything's going on. So this will get the closest, brightest nearby stars that would be candidates to have the transiting planets. So Sarah Seeger at MIT is one of the leaders of this, and very eager to see this happen. So we'll do that. And then here is an illustration of a spectroscopy that we do when we get a transit. Star has the planet go in front. The starlight goes through the planetary atmosphere on its way to our telescope and spectrograph. Spread out the light into a rainbow. We see spectrum lines. Those spectrum lines tell us the chemical constituents of the atmosphere of that planet. So this is now our way to hunt for signs of life out there. Not easy, but not impossible. So here's an illustration of the spectrum that you might be looking for. Lots of bumps and wiggles in the infrared spectrum, and each little bump and wiggle means something, a particular chemical, particular molecule or atom in the atmosphere of that planet. And so the depth of the ripple tells you how much of the material there is. The width may tell you what the pressure of the atmosphere is at that place. So lots to be learned from this method. But we still have to go into space to finish this. So this is an illustration of why this job is hard. There's Earth in front of our sun. And it's not really, but an artist drew it in there just to tell you how tiny we really are. Our Earth is 8,000 miles across. The sun is 800,000 miles across. That tells you it's going to be really hard to see. And when it goes in front, it blocks out 0.01% of the light. If it's standing off to the side, it reflects 1 part in 10 billion. So it's really, really hard to do this either way. Nevertheless, worth trying. So here's an illustration of what we might be hoping to do. Suppose you could block the light of a bright star by some method, and then you would see the row of planets in its little orbit there, what the picture is telling us. So there are different ways you could go at this. One is you can build a really perfect telescope and get rid of the light that came from the star so you can see it. And so we've illustrated some diffraction patterns. Remarkably enough, it's possible to defeat something called Poisson's spot. If you took electromagnetic physics in college, you would have heard about this. If I put up a bright object and I have a penny, and you try to block out the light of the bright object with the penny, then it turns out right in the middle of the shadow there's a bright spot. And this was predicted back in like 1800. And sure enough, it's there. And it's a proof of the wave nature of light. And this was shocking. at the time. Nevertheless, we have a way around it. Don't use a penny. Use a sunflower. Use something with pointy petals. And so mathematically it works. So this is an illustration that you really can do this. So how are you going to build a pointy petal thing? This is an illustration from Jet Propulsion Lab. They've been working on how to do this. So you need a telescope and a sunflower. Now, the sketch doesn't illustrate how hard this is. Because after you got it unfolded, you have to separate them by like 30,000 kilometers and then line them up perfectly so that the sunflower casts the shadow of the star onto the telescope. And then you'll be able to see planets zooming around behind it. That's not impossible. You can do this. It means, however, that now we've got an interesting mechanical engineering challenge. How are we going to unfold that sunflower? So, it can be done.
How big is it?
The sunflower needs to be pretty large, like 10, 20, 50, 100 meters across, depending on the wavelength that you're trying to study and how big is your telescope. So that's huge. Nevertheless, people have started work. So this brings us again to the spectrum that you might hope to learn about. At different wavelengths, you see different materials. Oxygen and ozone come at these shorter wavelengths. They're produced presumably by plants here on Earth. Water vapor produces infrared absorption lines a lot. We can pick them up with a Webb telescope. There's a change of color called the vegetation jump. Here on the ground, we have got green stuff, and it absorbs short wavelengths better than long wavelengths. So the Earth has a color as seen from a distance, and you could tell. And then there's carbon dioxide and methane that you can see out in the infrared. So all of these things would tell you whether or not the planet you're looking at is like home. So let's find out. So this tells you how hard the job is. You can look back at home from 4 billion miles out with our little Voyager. And what we see here is the Earth orbiting within the interplanetary dust cloud, which is pretty bright, actually. This is one of our big hazards about looking for planets out there. Because if they're sitting in a glowing cloud, it's kind of hard to tell that there's a planet there. On the other hand, the cloud tells you something. So, anyway, as was mentioned, the Earth is really faint compared to its home star. So, making very hard. So, I think we have a movie of the deployment of a test device. Out at JPL, here it is, slowly unfolding. You figure out how to wrap those petals around a cylinder, and it does come out. The big technology challenges here include that you have to have a pretty precise shape of that petal. It's like fraction of a millimeter accuracy. But this is not like nanometers, which you would have to build an optical system. So this is just a really good, tough engineering problem for mechanical folks. And they tell us that they can do it. And I've actually seen this pedal, this practice pedal has been on travel. It was brought around to the Goddard Symposium last March. So it's not all completely hot air on our part. We do know how to do some of these parts.
What's the material?
The structure is carbon fiber. And the thing is made opaque with, in this case, aluminized plastic. Probably Kevlar or Mylar, most likely for now. Anyway, it works, can work. So then how do you know that sunflower is going to work? So what they did was they set up a test out in the desert. So you got a light source, you got a star shade standing up on its tripod, and you go off and take a picture of how good was it? Did light come, was it suppressed according to the mathematics that we think we understand? And not exactly. You see there's some little bright spots where it should have been dark. But nevertheless, even so, they're able to simulate a planet, and sure enough, it would have worked. So this is the small version. If you want to put the coronagraph inside the telescope, there's a whole other batch of technology that's required. Here is a very tiny piece that you put at the focal point of a telescope, and it can be used to suppress the starlight and look for a planet. And you have to hook it up and adjust it, because no telescope is good enough. So what we have to do is measure whether the waveforms that are coming in from the star are exactly as they should be, and then fool with them, adjust them, using a sensor and a feedback loop to make the starlight go away. So it's possible to create a dark shadow of the star and look for a planet that's hidden in that dark box. So this works and has been tested in laboratories. We've got people here that work on it. Jet Propulsion Lab has been very big on this as well, and they have a facility where they can actually demonstrate real hardware doing this work. It's not all just math. So there are a lot of ways to go at it. We will be having at least some versions of this on the JWST telescope when it flies. So the first time that we have one in space that's capable of doing that job. So expect that it'll be really, really faint, but nevertheless try. So coming back to the Webb telescope, just to tell you that we're getting along, we have already led the way towards getting bigger telescopes. When they told us we needed these are 1.3 meters across, and each weighs, well, it's light enough you could lift it. So it weighs a little more when you support it on its framework, but it's still liftable by one human being. That's pretty amazing. The Hubble mirror is thousands and thousands of pounds, and it's thick glass, even with pockets cut out, is still very heavy. So no way could we make one of those do this job. So we know from our experience that it's possible to do more, make the material thinner, and still have it be the right shape. And so eventually we would like to have a much, much bigger telescope. So roughly 16 meters, something like that. We do not know how this is going to be put together because this is clearly bigger than the rocket. That one's a challenge. It fits snugly into the top of the rocket. If they build the Space Launch System, which is a lot bigger, maybe this will be easier. But this still is not going to fit into the rocket without folding up. So that's the challenge, is to get that one up there. So it'll lift more. Anyway, that might possibly adjust this target, but eventually has to be big and very light. There's one strategy people have been pursuing already, is to make a really thin material that you can replicate. It's not the only way, but this is one way. Make a big mandrel, make something that'll keep its shape if you copy it, put some ribs on the back, and that's one way. There are plenty of others. So this is what we need to do eventually. There's a whole lot of different ideas for how to do this. There's a smallish one, relatively speaking, 9 meters, and then the big one. But eventually you hope to get it to go up on one of those. I must say, though, it's easier to draw it than it is to build it. Clearly, that's something that we don't know how to do yet, but we should learn. People have been pursuing alternatives to big reflectors. This is a diffractive telescope. You probably know, you've heard all about Fresnel lenses. We have these little cheap magnifiers that you can put in your wallet. If you do it very carefully and just use the diffraction and not the little ridges, you can make something that's extremely good. So you can make a membrane and cover it with the right pattern of light and dark, and get a pretty darn good image. So this is under exploration. This one is called the Moiré, and this shows a graphic illustrating how big are the telescopes compared to the Spitzer, which we have up there, and the Hubble, which we have up there, and how big you might possibly imagine building a membrane kind of telescope. So maybe we won't use it for astronomy. Maybe people will use it for looking down at Earth. But at any rate, there are amazing possibilities there too. So eventually, we're looking for Earth 2.0. Is there another one of ours out there? it is calculated that there are not very many. There may be a lot of planets the right size, but we have a very unusual circumstance that we think in our solar system. We have continents and oceans. We have we have tectonic plates that move. We have an internal dynamo in the Earth, probably all related to the fact of having a very large moon coming from a collision with something shortly after the birth of the solar system. So we may actually have the only one. That's interesting too. It'd be nice to know whether this is really, really the only one or not. So eventually, we want to check out a lot of places. We know where all the stars are that are close by. We know exactly where they are and how far away they are and how many of them, well, some fraction of them would have planets. So a small number of them could be seen with a small telescope. A bigger telescope sees a lot more. And a much bigger telescope sees a whole lot more. So the hard question that we all have as astronomers and as engineers is to say, well, how much is enough? And that depends a little bit on what you think the probability of finding a Earth-like object is. We know how many there are the right size. We don't know how many are like us. And so that's the big challenge coming. We know how to calculate their temperature. We know what the Kepler Observatory has told us. Most of the ones they can see are hot, because those are the ones that are easiest for them to detect. But there is this habitable zone over here, and some of them, they found some of them. So we know where they are. We know there are a lot of them. We don't know how many will be like home. So there's the stars. So they're probably not all good homes for planets. Some of them are too hot or too cold as stars. Now, if you're lucky, some of them have an Earth-like planet, and most, anyway. If you have a really big telescope, maybe you can get 100 or so that are a lot like Earth. And that's why I think we should go for the big one. I think that's just much more guaranteed to be exciting. But it's pretty hard to do. Because there's the geometric challenge. So how are we going to get that up there? Something like that. One big rocket may be enough if we build the Space Launch System and finish that off. It would be quite useful for us to have. Not only could we build our telescope, we could get probes out to Europa in a hurry. People say that's a good place to look for signs of life under the ice. So we've got a timeline, but we don't know how long this next part takes. Need help. This is a big project. Anyway, I'll be happy to take questions about what we're going to do next. Thank you. Thank you.
Given that, based on Hubble, you determined that the age of the universe is 13.8, do you envisage any possibility that James Webb may prove that not to be accurate?
Oh, so the question is, since we measured the age of the universe already with Hubble and also actually with some other equipment like the cosmic background experiments, would we expect a change of that number from the Webb? And I think the answer is no. We have such tight measurements already that it's hard to imagine that they were all incorrect. So we'll find out, but I'm not expecting that surprise. Other surprises I'd be happy to have. Okay, other questions in the... There we go.
Yeah, so I know that James Webb Telescope will be sent to L2 point, and what's about new telescope? Is it L2 the best?
It's yes.
Telescope as well?
So the L2 point is chosen for the Webb telescope because it's the first place where you can go where the Earth and the Sun are always in the same direction, so you can put up your one-sided umbrella and protect your telescope, which you want to do either to keep the telescope cold, like the Webb, or to keep it perfectly dark and stable, as you would need to do for the new big telescope. So it's probably the right place. If you send it another few feet farther out, it'll eventually escape and go away from Earth. If you let it stay a few feet closer in, it'll fall back towards Earth and have some kind of interesting chaotic orbit. Anyway, you wouldn't like that. So it's the boundary between Earth orbit and solar orbit, and that's a good place. In the back.
So is the main driver to go bigger to increase the number of photons or to increase the spatial resolution?
So the driver for bigger is both, actually. Those little planets like Earth are so dang faint, we probably couldn't pick one up even if it was by itself right now, unless it was really quite close to us. So that has to be lucky. So that's number one. You have to get a bigger thing to get enough photons. We think to examine a stellar system, we're going to have to stare at it for a day or several days just to have a look to see if something's there. And eventually, of course, also to track down the spectrum. The spectrum of a planet tells you the details of the chemistry, but you have to have a lot of photons to do that, even more than it takes just to detect it. So mostly it's because the things are so dang faint. But if you don't also have a big telescope, you can't suppress the starlight enough either. So both reasons. I'm
wondering what other scientific objectives James Webb Space Telescope has. You seem to be emphasizing solely the exoplanet search.
Yeah, actually the Webb telescope was originally conceived for cosmology. That was seen as the hardest possible problem. And required, clearly, a big telescope that could do infrared to follow up the Hubble observations. We didn't know at the time that there would be planets to see. So it was designed entirely without that in mind. We're lucky that the things that we had already decided to do are powerful tools for planet studies. Webb telescope will be used basically for everything that people propose, from the most distant galaxies to the solar system. And we think it'll be good for everything. Also, if we build this bigger telescope, it would probably be like Hubble with a general purpose instrument package capable of just doing whatever Hubble does, only far better. So 50 times the collecting area, whatever it was you did before, you can do in a flash. So, and you should be able to watch the weather on the planets around our own outer solar system. You see a whole lot of stuff. You can watch the weather on Titan even from here. That's sort of amazing. You don't always have to go in person to visit.
You used the figure of 200 light years to search for Earth-like planets. Why 200? Why not 100? Why not 400?
So why the distance to search? Well, we know where they all are. So it's how far do you have to look before you get enough candidates? That's the big question. And so how much is enough? Are you feeling lucky? Do you think there's another one just like us nearby? Or do you think that we're rare and the special circumstances that we have will only turn up if you find a lot of candidates? So I think to be safe on the scientific side, you like a lot of candidates. But to be safe on the budget side, you got to make sure you can do it. So nobody's tried to design this really. This is too hard for us to settle on a design. But we've got to work on it, and we've started. People have been starting to work on these ideas for a long time. So hoping to get there.
Thank you. Bob, you had a question?
Yeah. So I'm wondering, can we make any improvement in mapping through its indirect effect dark matter?
Oh, yeah. The question is about mapping dark matter better. And of course, we map it by its gravitational effect. So with the Webb telescope, we can see its gravitational effect farther out. We can see how the galaxies were being pulled together. The earlier times, it was much more controlled by the dark matter than it is now. When we start with the map of the cosmic background fluctuations and all those pimples of the universe, most of those are dark matter. And the dark matter pulled the ordinary matter in to make galaxies and stars. So that's a very important question for us. How important was the dark matter as a function of time? And what was it doing when the universe was young? Probably a big deal. The movie that I showed you has predictions Different colors are showing the dark matter and the ordinary matter in that movie. So got to check that some way. But we still can't see it. It's still dark, still transparent.
Instead of building a big one, what about building a lot of smaller ones and combine them? Wouldn't it be easier and cheaper, and you could replace them with time?
So the question is, could you build a collection of small ones and combine the light? And actually, yes, you can. The reason to do it would be to get better spatial resolution, sharper images. And we actually worked on a concept for that that would have, I think, roughly 30 1-meter collectors. And it was built to image the surfaces of stars. If you like to see whether the stars like the sun are actually like the sun, do they have flares and sunspots, then you need what we call the stellar imager. And we did a study of that, and we know roughly what it would take. But it's not the same science that it does, and it cannot replace the big single aperture for that purpose. It would not be able to see Earth-like planets around other stars. So, on the other hand, what we might want to do is to take your idea, that idea, and say, well, can't you replace the mirrors on this new telescope if they're wrong? It should make it possible to assemble and maybe service the whole thing in space. Congress got really worried about our Webb telescope and said, isn't that kind of crazy not to be able to service it? And the answer is, yeah, that's the only choice we had. But the next one, they said, please don't do that again. Please make sure you can fix it if it's wrong. So you got to figure that out. Have to have some kind of space servicing for that giant thing. I'd like to see it last for 50 years. So it's going to get tired after 50 years. So we got to be able to fix it when it breaks.
Or just improve it.
Or improve it. Yeah, we improved the Hubble over and over again. When they first conceived it, what we had for imaging was Vidicon tubes. Do you remember Vidicon tubes? Then they got to put CCDs up for the first time. And now we have the most astonishing stuff up there that counts photons practically. So, question there. Go ahead.
Oh, me?
Yeah.
It's a fundamental question. So, how many habitable planets do we need at the same time? Because we are right now living on one Earth, but maybe every 50 billion years, maybe the planet will end. Then probably 1 or 2 habitable planets should be, I think, enough. But
right. So well, there are different kinds of questions about what's enough. One's enough for us, as long as we take care of this one. And we have 1 billion years before the sun gets too hot for us and we can't live here. That's a nice long time. It's not infinity, but it's still a long time. As far as I can tell, it is not possible for us to get to another solar system with anything that we can imagine building. We don't have wormholes, only in the movies. So you could imagine, however, that a robotic equipment could be built that would not run out of patience and could go to another solar system and start something. When it would get there and it could send information back to us, we'd have to be very patient too, because it wouldn't get a signal back for thousands of years. So I don't know. That's a hard one. So we better take care of this one.
Yeah, John, little change of pace. Reflections on your experience, which might be useful or interesting to the scientists, no matter what they're, and engineers, no matter what their specialty is. Reflections on leading a big international issue. What were the challenges?
Oh, the challenges of an international partnership. Okay, well, the first challenge was when we announced to the world that we were interested in partnership, they laughed at us because they said, obviously you don't know how hard this is. And they were right. But they said, we want to play anyway, because they knew that we would eventually figure out how to do it. So Europeans said, yes, we want to play. Canadians said, yes, we want to play. And then it took many, many years of negotiation before we were able to say which part each agency would be able to sponsor. And then the last hardest part was getting our agency to agree to the European contribution of the rocket. And a certain NASA administrator, who I'll not name, refused to accept the European contribution of a rocket. And when we got Mike Griffin in, he said, yeah, I understand, we better get that. It took him a few weeks to make that decision. So there are a lot of tricky things about international stuff. But on the other hand, I think in this case it's definitely worth it. Europeans are able to bring their own resources to bear and take on challenges that we would perhaps be afraid of. Because we got a hard enough challenge as it is with the part we chose. So definitely I think it's worth having the international partnership for big projects, even though negotiating them is troublesome. Nevertheless, I really think it's a good thing to do. And it's also fair. If they're going to use the telescope, can't they help pay? So that's how the Europeans got to use the Hubble. They helped pay. But then, of course, we let the whole world propose to use it anyway, because we really want the best science. But still, it's fair for them to pay. Does that address your interest? Yeah, okay. More thoughts? There's in the back. Okay.
I was wondering what your thoughts are on kind of recreating the iconic nature of the Hubble with the James Webb to make sure that the interest of the public in the astronomy that was been done by the Hubble continues on with what the Webb's going to do in the future, because Hubble had an interesting story that helped make it be what it is to everybody. So I was wondering what your thoughts on that, how we do a good job of making sure JWST does the same thing.
Well, I think our strategy for the Webb telescope and its public impact is to build a great telescope and do great science. Because we don't control the media, we just tell them the good things that we did. And in the case of the Hubble, the media were especially excited about it because we almost wrecked. There's nothing like nearly dying to get people's attention. And of course, servicing with human beings in space is also dangerous. We almost didn't do it the last time because it was so dangerous. And then again, we had to get a new administrator to make that decision. You know, your life is at stake with the Hubble more than once. With the Webb telescope, it's just the life of the telescope that's at stake, plus all of us who would be extremely, extremely, extremely upset if our project didn't work. So I think that the science will stand on its own, and we won't have to do anything special to get public attention. When the telescope was almost killed for budget reasons, about 3 years ago, members of the public that we never heard of rose up and started a campaign to save their telescope. And Congress didn't even know anybody thought it existed yet. So the fact that the public already knew and cared deeply means a lot.
Did you refer to the Webb?
The Webb telescope, yeah. It happened before, of course. There was a time we weren't going to service the Hubble telescope, and the public rose up to save their telescope that time, too. So the public actually cares deeply. At least some of them do. Some of them care very, very deeply. And they would do anything to help us.
Last question here.
Okay.
Oh, sorry. You had mentioned we have to go to space to do all these things, but there's another path, like you could stay on Earth, build huge telescopes and use adaptive optics. That's not the path forward?
Yeah, so his question is, why can't we do the planet discovery with adaptive optics telescopes on the ground? And calculation says it's too hard. We do have planets that can be detected and have been detected with adaptive optics on the ground. There's a wonderful system on the Gemini Observatory, and the first time they turned it on, it saw a planet. Like that, because they did a good job of the engineering. But it's just really tricky, because the atmosphere is really shimmering all the time, and the planets you're studying that are like Earth are really faint. So all the calculation says we can't do it. So we will surely try, because we've got the equipment coming. We've got 3 giant telescopes coming. Then none of them have been finished, but all have been started. The European one is about 40 meters across, and 2 American ones about 26 and 30 meters across. So those are truly huge, and they are happening, and surely people will try everything they can when they get that. But calculation says it's still not enough.
Spectral analysis is really hard.
So anyway, it's hard, but they will try.
So I think with that, let's thank John one more time for